Thank you, Janet. And also welcome everyone to this training course on the particle size measurement. So just a sound check that everyone can hear me and can see me as well, hopefully. Okay, I see a few thumbs up. Thank you. So what we have prepared for you the next 3 days are going to be some basics and also some applications related to the particle size measurement. So we trying to prepare this course specifically for you who may be doing reviews, who frequently see the applications containing particle size measurement results, and you may wonder how to properly analyze and assess and to ask questions. So, so we prepare this course with that in mind. So hopefully you will find something useful with this course. And can you still see my screen? Looks like, can you see screen? Sorry. Somehow my screen shows differently now. Can you see the screen?
It's fine.
Okay, okay, thank you, because the screen changed. So before we start, just introduce a few things, logistics and housekeeping. So we do want to encourage you to ask questions. A lot of us, we don't know what we don't know. So especially that's true for us as well, who are providing training to you. So what we want to hear from you are the questions that you may find during this training, and also certainly what you have seen during the review. So please do ask questions, and you can put a question either into chat as we are going through the topics, or you can unmute yourself and then you can directly ask questions. That also works. And also what we'll do is we will ask you questions as well throughout this course. So want to make sure that you are not away from your computer and you are responding. So in terms of the response, you can again either put in chat or use the reaction buttons. So I will just do a practice right now. So everyone please go to the bottom of your screen and there's a reaction button and click the reaction. And I want to see everyone either do a green check, the check mark, which is yes, or a red check mark, which is no, or a thumbs up. So I want to see everyone turning green. Seeing, yep, almost everyone is responding. I see still a few. This is just to make sure that in the next few hours and next few days, we're going to repeatedly asking you to respond to questions, and we want to also see your reaction. So this way, we don't need to practice anymore. You can directly go to the reactions. Sometimes we will ask you to respond yes or no. So in that case, use the green for yes, red for no. Also, you can type in chat. Okay, thank you. I see almost everyone have responded, so great. Also, we want you to take from this course something that you find interesting. So we're trying to keep this course as interesting as possible. I know training sometimes can be boring. So we tried really hard to make this interesting. And also we prepared a lot of information for you in the training slides and also some examples. So we will share with you that after the training, and also you can actually see some of the PDF document already uploaded to the calendar itself. But what I would ask you to do is try not to open up the PowerPoint slide PDF right now, because what we want you to do is listen, try not to jump ahead of the slides. We will do a lot of explanation. So the PDF document will be available even after the training. We can share a combined document just so that we want to you have that material, but try during the course itself, try to listen for the most. And yes, and the slide would also be sent, have been sent through the invite this morning. So also, we want to hear from you in terms of how we are doing with this course. So we will send out a survey by end of this course So please do fill it out. And it's very important that we hear from you the things that we can improve in the future. And also, I want to emphasize that we are here to support you. We are in the Office of Testing and Research. We are a laboratory-based office. So we routinely provide trainings like this to reviewers. But sometimes we recognize that during the training itself, we cannot provide all the information that you need. And also sometimes we don't know maybe the solution to the problem that you are working on. So we are really open to work with you even after this course. So don't worry if the things that we're trying to put into the course in the next few days may be too much or maybe too little. Recognizing that even after the course, we're still here to support you, and feel free to reach out to us, and we'll share with you the contact information by the end of the day today. So we will have a session to explain to you who are the contact you can reach out in case you have questions. And of course, I cannot do this alone, and I have recruited a few presenters to work with me today and for the next few days. Actually, I should putting them here for now. They're Billy and Hayo, Max, Naresh, and Shane. So both Naresh and Shane will be moving from OTR to other review offices. So in case you come from OPMA, you'll come from ONDP, those are your new colleagues that you will have who are very familiar with our OTR resources. So they can be a great resource for you in terms of the contact. But in terms of the agenda, again, for this training, so today, this morning, we will cover two topics. One on the particle size concept and the light scattering phenomenon. And then we will follow by presenting or discussing the dynamic light scattering, which is the most commonly used sizing technique for nanomaterials. And then we will end the day with a tour of our laboratory virtually and to show you our lab, and also again highlighting a few just capability-wise. So that will conclude the first day this morning. And starting tomorrow morning, we will start with talking about the laser diffraction, which is the most commonly used sizing technique in pharmaceutical applications. Even though dynamic light scattering is the most common for nanomaterials, laser diffraction is by far the most commonly used for all material characterization. So we will spend some time in the morning to talk about laser diffraction. And then we will talk about a rather advanced and new technology for analyzing particles, especially submicron colloidal materials, called a fluid flow fractionation. And follow that, we will talk about subvisible particles. Essentially, we will talk about undesired particles that may be present in the drug product. So that'll be tomorrow's schedule. And for the last day, we will start the morning, talk about the method of validation. And you may wonder, is the same validation that we have been using in the ICH guideline or the USP guideline, is that suitable for the particle size measurement? And the short answer is no. So we will talk about what is more appropriate for validation-wise, for validation of the particle size measurement. What are some of the key points need to be considered? And also I will talk about some of the common deficiencies. So Wednesday morning, we will conclude the Wednesday with a breakout session, 3 breakout sessions. So we will give you a few very interesting examples, and we will have a few instructors work with you in the breakout session to basically use what we have learned in the last 3 days and to put into use and to actually finding what is the problem and how we would flag it to ask the deficiency question to the applicant. So really encourage you to be more involved in the discussion. That's the agenda for this training for the next 3 days. With that, I will again tell you what our goal for this course is. Sometimes you will look at the application, you see the report like showing on the left, and you may wonder, where should I look, or what results, what value, or what parameter should I look? And is there any problem with this data that's showing on the left side of the screen. And this may be very common during the review. So throughout this course, what is our goal is to help you understand the basics and the theory behind the size measurement. Again, we will cover a few topics: dynamic light scattering and laser diffraction, AF4, and also subvisible particles. So we'll explain the basic theory. And also we will help you to understand the basic limitations of each sizing techniques, recognizing not one single technique is universally applicable for every applications, and every technique has its own limitations. So we will introduce to you to be familiar with those limitations. And also, we want you to be able to analyze the data and draw the conclusions by looking at the figure on the left. And most importantly, perhaps, is for you to feel really comfortable asking questions to the applicant and be comfortable that the question you're asking is sound and you know exactly what you expect the applicant to provide you back in order to address that concern. So again, this course is designed for the reviewers in order to do your job, make you feel more comfortable doing it. Okay, that is my introduction. So I will start the morning again by talking about the particle size concept and light scattering phenomenon. And this first part of the training is a little bit different because I know that very frequently we don't actually talk about philosophically what we are considering as measuring particle size. And typically we jump right into providing you procedures or details about how to measure the particle size. So this, the beginning of the day is going to be a little bit different. So I'm going to talk about, yes, the concept of particle size and why is it important to understand that. So we will cover a few concepts and also we'll talk about the light scattering phenomenon. But before I move to the next slide, I want to, now it's a time to be interactive. Be ready, put into your chat or put into your reactions. Maybe I want to see a show of hand. How many of you think that particle size measurement is simple, is straightforward? And if you do think that is simple and straightforward, you can use reaction green button. Or if you think that particle size measurement is complicated, is challenging, and you can use the red button to show. So it's a trick question. So, please do a show of hand. And let's just, okay, I see quite a lot of red, which is reasonable. You are here, and a few green as well. To be honest, for myself, many years ago, I started preparing for this course. When I was preparing for the course, I was thinking that the particle size measurement is very simple because I've been doing that for years and how hard it can be. And then I started preparing material for teaching. And then I realized it's not as simple as I thought. So I'm going to explain to you why that might be. Hopefully I can get you to agree with me. So first, I want to cite a statement from a paper showing on the bottom of the screen. That's the reference to the paper. And in this paper, it is consolidated collected a lot of comments and the feedbacks from the industry in the field of particle size measurement. And in the end, it posed as this statement, which I totally agree, and I think captures the reason I feel why it's not as simple as I originally thought. So the statement is that particle sizing is actually a very poorly posed problem. The apparent simplicity of particle size analysis is very deceptive. So if you think about the size measurement is simple, you may be thinking from the measurement perspective, putting the sample into an instrument and you can get a readout very quickly in a few seconds. So the simplicity of actually measuring particle size is very deceptive. The difficulty, the problem is actually why do we measure particle size and what we are actually measuring, right? So for me, over the years, I've generated my own thinking around this topic, this statement, particle sizing is a poorly posed problem. So I further define this in two aspects that I'm going to share with you next. So these two statements may seem very provocative and controversial, but believe me, it's something that I've accumulated over the years. So the first part of that is what we are truly interested is not the size, right? So even though we are measuring size, but what we are actually interested is not the size. So that's why there is a disconnect, why there's a challenge. And the second part is that what we are actually measuring is not the size. So that may seem really strange that we're measuring size, but what I'm saying that we're not actually measuring size. So hopefully throughout this course, after this course, you would agree with me in these two statements. And I will, start by explaining in this morning the first part. What we are truly interested is not the size. And later on through the next few courses on dynamic light scattering, laser diffraction, AF4, and subvisible particles, will give you more information about what we are actually measuring. Is that the size or something else? So let's look at the first, what we are truly interested is not the size. So with that, I want to now ask you for interactions. So please put into the chat, what do you think or come to your mind of some of the examples about the particles that you see in your review or you've seen in publications? What are some of the particle examples? And you can type into chat and I can see the chat. Protein aggregates, great. That's something that undesired, right? We know we want to have protein biologics. We definitely don't want to see aggregates formation. Liposome, great. Suspensions, injectables, salts, precipitate, undesired. API, great for the solid oral. Granules, micelles, DPI, MDI, yes, for the inhalation product. Micelles, yes, surfactant form aggregates, which is desired. Dendrimers, great, polymers. And globule of emulsion, yes, ophthalmic emulsions. Unstable aerosol, again, undesired particles, but aerosol may be desired if it's for inhalation. Nanoparticles, clearly, yes. We have many products in the submicron domain that are particles, liposomes, micelle, emulsions, and emulsions, yes, globule distribution, crystallization, particulates, yes. Sometimes can be desired crystallized crystals as in API manufacturing, but also sometimes the particulate formed undesirably because of the limited solubility, right? So thank you for interacting. Thank you for putting that feedback. So that's really great. So as you can see, there are yes, a lot of particles. Actually, you all typed in many of the examples, starting with API material. We have maybe API powder that in the micron domain or in the submicron nano size range, and also excipient. All the excipient most of the excipient are powder materials. They are mixed with the API and maybe form the granules, whether either through wet granulation or dry granulation process. They form larger granules, making from smaller to larger. And also suspension that can be really small, that can be suitable for intravenous injection, or can be very large for topical applications like ophthalmic or oral. And also emulsion, I've seen examples like can be used for ophthalmic topical use or oral emulsions as well. And aerosols and used for nasal inhalation applications. And of course, a lot of nanotechnology product like liposomes, micelles, protein drug complexes like Abraxane, paclitaxel product, as well as lipid nanoparticles, which is a more of an emerging kind of technology product we know have been used in the messenger RNA COVID vaccines and iron colloids. And also the bottom, there are a few undesirable particles like a particulate formed from the proteins or from oligonucleotide that are both visible and subvisible particles that are undesired. Or in some cases, we have seen glass laminars, which is a byproduct of the container closure problem that due to the interaction between the glass and the content forming those glass laminars, certainly undesired, right? So we have a lot of example of particles, and of course, because of those a lot of applications, you see very often we want to know the size, right? We want to measure it. That's the reason we've seen it very, very commonly, and that gives the impression that something must be very easy to measure, right? So I'll start by explaining this not so nicely posed problem by first talk about some misperceptions about what are the particles. So I will start by talk about something that maybe you have not been paying attention to, and that is the dispersion medium. So, what is a particle, right? A particle is a very small or discrete fragment or unit of matter, and then can span the size from angstrom to less than 1 nanometer to really large to above a few millimeters. So particle is a really cover a wide spectrum of size ranges. And of course, when we talk about particle, when we talk about unit of matter, we need to recognize that there are 3 forms of matters. There is a gas, liquid, and solid, right? State of matter. So because we have these 3 state of matter, we actually have a multiple combination of type of particle that can be present. So something that's overlooked very frequently is the environment of the particles. So we would not think about this way. We would not have a particle if we don't have the environment that particles in. In a sense, a particle does not exist in the absence of an environment. Why is that? So if we think about, for example, a powder, granule, or aerosols, and those are solid material dispersed in gas medium. So in this case, the particle is a solid material, but the solid material is dispersed in a gas environment. So we also have suspension, like in the example you've mentioned, injectable suspension, topical suspension, or even glass laminars or other particulate, typically are solid material dispersed in liquid environment. Again, a material in a state in a different environment, solid in liquid, it's a suspension. And we may also have liquid in liquid. In this case, we may have an oil, which is immiscible with water. And when you put one into the other, we will form this dispersion called liquid-liquid dispersion. Typical examples like oil in water emulsions, O/W, that stands for oil in water emulsions, or water in oil emulsions, just reverse the order. But again, it's a liquid dispersed in liquid, so a particle with its surrounding environment. And further expand to liquid in gas, we can have a nasal spray, a liquid droplet dispersed through a device into the nasal cavity. And that's also a particle, but here the environment is gas, it's air, it's the dispersion medium. And also we may have some what we call sometimes soft matters. They are neither the solid nor liquid, but they are in between. This example include liposomes and micelles, and you may consider either solid or liquid in this case. So why does it matter that we need to pay attention to the dispersion medium? And the reason is, very frequently, when we talk about the measurement of particles, we need to talk about how do we present the particle to the measurement instrument. So we certainly need some procedure to prepare the material for its measurement. And recognizing that if you change the environment of the particle that is come from, there may be some property that will be altered, the particle properties. And one example, for example, if we are measuring a powder material, and API is a crystalline powder. And in order to measure its size, let's say we want to put into a laser diffraction equipment. And in this case, let's say we have a liquid dispersion unit. So now, if you need to disperse the powder material into a liquid, essentially you are changing the environment from gas to liquid. By changing that environment, something will happen, right? For the solid material, it's easy to recognize that the particle API either will dissolve if it's a drug, piece of material has enough solubility in the liquid, or it will aggregate and form irreversible aggregation or agglomerates, which may be reversible. So the point is, by changing the environment, we may change the property of the particles, leading to some maybe undesired behaviors that will interfere with the measurement of the particles itself. So in a way, when you are trying to measure the particle size or measure the particle properties, if you need to change the environment, you really need to pay attention to what was the original dispersion state. So this, I think, is a kind of overlooked concept. In many of the particle size measurement, we see very often the either applicant or researchers do not pay attention to the dispersion environment. And because of that overlook, we really have some unfortunate situation that the measurement procedure, there are clear errors that can be easily prevented or avoided. So for you, what's important is that whenever you see a particle, in your applications, first thing coming into your mind should be what was the native environment of that particle, what was the native dispersion medium, and what is the dispersion environment or medium that is used during the measurement. Does those two are those two different? If they are different, then pay special attention to the potential changes in the properties like stability, etc. So pay attention to the dispersion medium. Next, we will further look at a few examples, and I'll explain to you why size is not the only thing. So first example we'll look at is micelle. What is micelle is a self-aggregation, self-association colloid formed from the surfactant. So the individual surfactant, due to their shape, when you put into water, again, the environment is aqueous, is liquid, and you disperse this molecule into liquid, they do not have, they want to self-associate to minimize the hydrocarbon chain exposure to water. So they form this aggregated form called micelles. And micelle size-wise is about less than 30 nanometer. And thermodynamically is a stable system. It's spontaneously formed without any energy input. And also when you dilute this micelle system, it will change relative to the concentration. And there is a threshold below which the micelle do not exist, and that is called critical micelle concentration, or CMC. So that's the first type of particle we're looking at. The second type of particle is little bit larger. This is liposomes. And in pharmaceutical applications, we have seen most of liposomes are in the size range 70 nanometer to about a few hundred nanometer. And they are kinetically stabilized in a way. If you leave the liposome sample for over 1,000 years, probably don't even take 1,000 years, they will become destabilized and they will revert back to their most original stable state, which is a bilayer configuration. The reason why is the lipid, which is shown on the top of the individual component, they are cylindrical shaped. So the most ideal configuration for them to stay in a liquid environment is to form a layer by layer structure rather than a spherical structure. However, due to some kinetic constraint during the formation of liposome, they will assume this spherical shape. And so therefore they are kinetically stabilized. They are not indefinitely stable. And because they are such a kinetically stabilized or trapped system, they are very, very stable against dilutions. So if you dilute a liposome 1,000 times, 100,000 times, it will not change the stability because the lipid, how they arrange into this structure is kinetically trapped. They do not want, the lipid molecule do not want to leave the liposome vesicle to form another structure. And another example is a dispersion of liquid in liquid, in this case, oil droplet dispersed in water, forming oil in water emulsions. The size of the emulsion can vary from small, 20 to 30 nanometer, to really above 1 micron, we call coarse emulsion. So the size span a very wide range. And again, they are also not thermodynamically stabilized. The reason is oil and water naturally want to separate into two separate phases, minimizing their interfacial area. So a two-layer has minimum surface area, but when in this globule form, actually there's a lot of exposed surface area. So giving enough time, oil and water will separate into two layers. But again, they can be kinetically stabilized to remain in this oil and water emulsion for a short duration, typically many years. So for pharmaceutical applications, this is certainly long enough to have a finished drug product given to the patient. And due to that, it's not a thermodynamically stabilized system. It's very prone to destabilization like agglomeration, coalescence, also a ripening and phase separation, etc. And as we can show you, we will show you something example later, that dilution may alter the measurement outcome of the globule size distribution, but may not be what you thinking it is. So we will explain more of that in the later portion of the lecture. So as you can see, I gave you 3 examples here. One last one is something very different and strange. It's called microemulsion, and it's also called swollen micelle. It is a thermodynamically stabilized system. So its size generally overlaps with nanoemulsions, which is again few hundred to 1 micron. But the formulation process and the processing conditions are totally different. Indeed, the last year we have actually worked on one of this product, looking at determine if a product is it an emulsion or is it a microemulsion. So it's a very interesting study. But the point I want to show on this slide is you heard me talk about many things about the particles, but you recognize when I talk about the size, it's only one aspect of the particles we're looking at. Indeed, size is only a small fraction of what is a particle. And there's so much more to the particle that we need to pay attention to, like how it is made, what's the composition, what is the stability, and what's the factors govern its stability, and what's the manufacturing process leading to the formation of that, what's critical going to the making and the stabilization of those particles. So as you can see, there are many things going beyond just the size, and size is only one part of many attributes of the particles, right? So with speaking of that, the properties, so it's another interactive way. Now I want to ask you for a few questions. So what properties or functions come to your mind when you think about particles? So let me actually, of course, you may think about particle size as very obvious. We're talking about today's class, or dissolution. And let me just exit my screen. So I want to hear from you and putting some of the response. Sorry, I see I missed that there are a few questions. Let me see. I don't see gas in liquid. Gas in liquid. Yes, gas in liquid, that's also possible. We have well, in the academic research, there is a formulation called microbubble, so which is a gas dispersion in liquid. So yes, it's also possible. So liquid can be the dispersion medium, gas can be the particles, in this case, a bubble. In a gel dosage form, can I consider particle state as solid in liquid environment? So I guess the question is, what is a gel? The gel typically is a polymer solution that has some viscosity. So typically, yes, it's a liquid, but the question is, what is the particle? The particle can be actually a solid material dispersed in the liquid. So for example, we can have an ophthalmic gel. One example is Lotimax, which is loteprednol as a particle dispersed in a gel, hydrogel, and then so the particle is the solid and the liquid environment is what's giving that. How sensitive are the micelles to the dilution? How stable are the liposome to the dilution in general? So micelle generally will remain as micelle unless, as long as it's above its critical micelle concentration. The micelle will not exist when it's below the critical micelle concentration. When it's below the critical micelle concentration, surfactant, which is the individual building block of the micelle, they will just occupy all the available surfaces. So they will form a monolayer coverage of all the interface so that you don't have basically excess of surfactant forming the micelles. How stable are liposome to dilution in general? Very, very stable, relatively. And this is because of the kinetic, again, it's because the liposome system are trapped in this configuration association that for any single lipid molecule to move away from the liposome to into the solution is entropically forbidden because when the lipid goes into water, it's going to interact with water. The hydrophobic tail will interact with water, which really lowers the entropy of the whole system, which is unfavored. Okay, so so now, sorry, I start looking at, sorry, my screen a little bit small, so I cannot see all the comments, so bear with me. Solubility, that's good, particle solubility. Let me put solubility here. And particle shape. And charge, right, size and shape, composition, affinity, maybe affinity of the particle to something else, right, to protein or to affinity to another surfaces, right? And BU and CU. What's BU? Is that content uniformity and sorry, can you type out what's BU? Is that content uniformity? I will assume. Sorry, I'm really behind. Just so many. Can someone speak up because I cannot keep up with the typing.
Okay, we have, Xiaomin, we have distribution.
Distribution.
Solubility.
Okay, drug distribution, maybe. Dissolution rate of
dissolution
yes.
rate. Surface charge.
Surface charge, we have that.
Density.
Density, great. Density.
UV IR absorbance.
Oops, sorry. UV IR absorbance.
Stability.
Stability, great. I was wondering, anyone will mention stability?
Okay, state of the particles. I think that's the last one. State of the particles.
Okay. Okay. Stability. Okay, great. Thank you for all that. Maybe I'll add a few here. Maybe I will add the composition, surface charge, particle size change, concentration above CMC. Okay, I assume that question still refer to micelle. No, the size will not change above the micelle. Shape, yes, particle shape is there. So I will add a few. I will add flow properties or flow in a pipe, for example. That may be relevant for a solid material. We need to process it and we need to compress it, right? Or maybe packing density or compressibility of powder material. And that is important for making them into a tablet and later on impacting the solution, right? And I see the dissolution rate, I will add their release as well. So oftentimes the particle will change, changing the particle properties also change the release. And I know we have today's many colleagues from OGD. And one thing I think in the OGD that's commonly really important is sameness, right? Equivalence, right? So how do we ensure one product is same to the other product? So when we're looking at a particle, we very commonly consider how do we compare sameness of the particles. So any more examples? I really appreciate everyone kind of respond and apologize. I was thinking I will be able to follow all the type up, but apparently you are very engaged into this discussion, so I'm not prepared. Concentration, okay, I'll put here, concentration of the particles, right? Yes, reactivity. Actually, let me put reactivity to here. I don't know whether you start to see a particular trend. What I'm doing here, adsorption. You start to see that I'm separating the particles, the properties, the function into two columns, right? On the left-hand side, those are the properties associated, mostly describing what is or what do you need to know about the particle, some of the properties. But something to the right is what does the particle do, or what is a thing that particle does that impact maybe what you do in the review, right? So one is what is this thing, the other is what does this thing do. So those are two different things. One is, again, you measure just simply what it is, but the other is, you know, why we're measuring this. So if you pay attention to what's on the right, we want to know what is the dissolution rate of the, you know, right, the particles or the product. We care about the particle size because particle size is directly related to available surface area, and available surface area directly impact the rate of dissolution or the release. And therefore, we want to know this particle size because we care deeply about the rate of dissolution because it's related to the bioavailability. Also, in the other situation, we care about the size and the shape of the particles because that influence how this powder material will flow in a manufacturing process. Does material A blend material with B perfectly, form a uniform blend, and in order to form this nice tablet with a uniform content. So in this case, we want to know the size of the particles. We want to know the shape of the particle. We want to know the density, the bulk density, the tap density of the particles, because that will allow us to assess the process capability and the quality of the product. So what we are really interested is the process in this case, right? Similarly, the dissolution. Or some other situation, we care about the stability. We want to make sure that the product do not show the aggregate formation throughout 2-year shelf life. We want to make sure that we have adequate method to detect the presence of the aggregate formation. So in this case, our goal is to detect undesired formation of the particles. So almost every single situation, when you are measuring particle size, there is a purpose associated with that measurement that is not the purpose of the measuring size. To summarize what I'm trying to describe here, I'm going to, let me share my screen again. I'm going to quote Professor Dr. Harold Haywood. So he described this, which I think is very well summarized what I want to say here, which is a particle size analysis is not an objective in itself, but is a means to an end. And the end being the correlation, what he stated is in green, powder property with some other process of manufacture, usage, or preparation. However, what you can do is replace those in green with the thing that matters to you during the review, right? So basically, you can rewrite this to particle size analysis is not an objective in itself, but a means to an end, and the end being the correlation, let's say, the size of the particles with the availability of drug in vivo, right? So we measure size not because we want to measure size. We measure size because size is important of the product that we are cared about, that some critical functions of the particle that we really want to know. And because that property is not easy to measure, we want to use the particle size as a surrogate to allow us to measure that properties or that functions or behavior. So it's a tool, it's not objective. So that hopefully you agree with me that when we are trying to measure size, we're truly not interested in actually measuring size. We're truly interested in something that about what the particles do, like dissolution, like stability, like process. So now I would talk to you about what we are actually measuring, right? So think about any analytical procedure. Typically we will be interested to know two things, right? One thing is how true is the value that we obtained compared with the value we consider as a reference, as the target, right? In a sense, how far away is our observed or measured value compared with the true value, the trueness, right? And the other critical aspect of any measurement, including particle size, is how precise you can generate the observations, the measurement. So essentially, there are two critical aspects to any measurement. One is trueness of the measurement, and the other is a precision of the measurement. So now I want you to go into your reaction. Sorry. I want you to type in the message. Do you think the trueness is easy to obtain for the particle size measurement? Then type trueness in your chat. If you think precision is easier to obtain, type precision. Sorry, I missed it. So if you think the question is which one is more difficult for you to obtain? Is it precision or is it trueness? Which one is more difficult to obtain? Sorry. Is it trueness difficult to obtain or precision difficult to obtain? So you will type the one that you think is difficult to obtain. Great, I see a lot of response already. Apology for me mixing it up. Thank you for, yes, trueness. Well, got a lot of, all of you are saying trueness, which is correct the answer. And I'll explain why trueness is more difficult to obtain. And on the other hand, precision is easier to obtain. So first, let's look at what is precision. So precision, I tend to look at it as three things, 3 R's. So these 3 R's are repeatability, reproducibility, and robustness. So 3 R's, the 3 words, the first letter. And anytime when you're thinking about particle size, when you're thinking about precision, just think about 3 R's, repeatability, reproducibility, and robustness. So what is repeatability? Repeatability is a closeness of agreement between multiple measurements of results of a given property, in this case, the size, in the same sample aliquot, executed by the same operator, in the same instrument, under the identical conditions. Only difference is time. First measurement, the second measurement, the last measurement, only difference is the time. Everything else, the material, the sample preparation, operator, machine, conditions, method, everything remain the same. For the repeatability, only difference is time. So this, what you typically see is during a lot of measurement, essentially is one measurement, we get multiple observations of that measurement, we call measurements in the instrument protocols. So what does repeatability tells you? If something changed, let's say one measurement from another measurement, there is a difference, right? Ideally, they should be the same, or they should be really, really close. But in case there is a difference, what does it tell you? It tells you either the machine is not working properly, right? This can happen. There's electronics or flow unit or something is not working properly. So as a function of time, you get a different observations, different values. So first thing that can tell you, hey, repeatability, we do not get the same result, can be means that machine maybe has some problem, or the method is not suitable. That can mean that we either we run too long or too short, or the condition is not proper, so sample are undergoing some changes during the measurement. So that typically lead to the third one is sample has some stability issue, that as a function of time, sample actually is undergoing changes. One classic example is measurement of laser diffraction. You put a powder material, as I mentioned earlier, you put a powder into a liquid, what happens is the particle will dissolve, right? So if the particle dissolves, what you will see is over time, the same sample, over time, the particle size actually will change. Sometime will decrease, sometime will increase. I'll explain maybe later. But the sample stability is another thing you can get by looking at the repeatability. So the same measurement, right? Same sample, same operator, same instrument, identical condition, differences in time. And this is repeatability. The next, reproducibility, something changed. So this change is either the, well, not either, we prepare a different sample, right? So we take from the vial, we withdraw another material, we dilute it and prepare two sets of sample, and we perform the measurement. So this is a different set of aliquot of sample, and can be prepared by two different operators and on different days, and may not be the identical equipment, can be the same principle but a different brand of instrument, or can be the instrument from two companies and two different locations, right? Sometimes they need to do the method transfer. So, or right, but in general, it's the same method they are applying. So what does the reproducibility tells you? Reproducibility tells you if the measurement is not consistent, it's not precisely the same, sometimes it's an indication that the sampling procedure has some problem, or the dispersion medium is not appropriate, right? Again, the environment, and also machine can be malfunctioning as well. So reproducibility is really good to check, again, the procedure, the method, dispersion technique, etc., whether or not it's appropriate. The last R is robustness. Essentially, now you need to actually deliberately introduce some variations into the measurement. What you want to see is that it's both sensitive, meaning if there's underlying changes in the size, you want to actually be able to see the size changes despite the introduced variation in the procedure. And this can be you adding the sonication, or you're changing the flow rate, or changing the particle concentration or temperature or whatever parameters that you can change. But also, you want to make sure that the measurement still is repeatable, generating the same level of signal to noise ratio, the same observation over time. So this is robustness. You are intentionally introduce some variation, looking for that sensitivity and the precision. So that's all I can talk about the precision. It's the 3 R's. As you can see, this is a matter of effort, that as long as one stick to the procedure, stick to the 3 R's, everyone can do the precision right. And as long as they optimize the procedure and pay attention to the instrument settings and making sure instrument is properly maintained, it's relatively easy to achieve the precision. So you typically in the validation report is that they will show day-to-day, analyst to analyst, and some robustness changes. Very rarely, actually, you see that the number are different. If they are different, then they got a problem, but very rarely you will see a problem. So much easier to demonstrate or to develop the precision for the particle size measurement. So what's challenging is to measure the trueness. So in order to explain this, so I will start with something that it seems very trivial. How do you describe the size of this basketball, right? You may think this is too simple. It's diameter, right? Or radius or diameter, very simple, it's a sphere. What about this? A cubic structure and the same length across. So also this one may be simple. You need one side of the lens, which you can describe the full, the shape of this structure. What about a football? It's no longer spherical. has some elongation. So now one parameter may not be enough to describe the diameter, right? So you might need a longitude and the longer length and also cut it in half the other perpendicular direction. So you may need two parameters to describe the size. What about the diamond? Right, this is a little bit strange shape now compared with the other three, but you may still be able to describe, I trust you'll be able to describe something, maybe by weight, right? The carat of the of the diamond. But what about this rock? It's irregular shaped and different mass. How do you describe the size? What is the true size of this rock, right? So indeed, if I take the last example about irregular shaped particle rock, I project it into a two-dimensional space like a paper. We draw the outline of this particle in this bolded dotted line, and asking you to describe the size of these particles. And actually, if you look at the USP 776, you will find multiple ways to describe these particles. The most common is what's called a Feret diameter. So that's the parallel line that's tangent to the particle. So you will just realign, and then you get a two parallel line, and then tangent to the particle, and then measure the length between these two parallel lines. As you rotate, the Feret diameter will change from minimum to maximum. Therefore, Feret diameter has a Feret minimum and a Feret maximum. Also, you may have Martin's diameter, projected area of the equivalent circle, or you can put a rectangular box around this object, minimizing any white space. So you will have a length and a width, what's this called bounding rectangle. And then you have a two diameter describing this one single object. But the point I want to make here is that for irregular shaped object, a two-dimensional object, there's not one way to describe the size of it. There are many ways to describe the particle size. Any way of those described here is correct, right? So if I further expand to a three-dimensional object, right, from two-dimensional to three-dimensional, we see a little bit more challenges now, because we no longer have, just a two-dimensional descriptor of the size. Now we need to, how do we describe a three-dimensional object? Unless this three-dimensional object is a sphere, right? An oil globule, perfect sphere. Liposome vesicles, most of liposome are perfect spheres. Air bubbles, mostly are spherical. So basketball, spherical. So for a three-dimensional object, if they just happen to be a sphere, it's easy, relatively easy to describe its diameter, because all we need is either a radius or diameter to describe it. So that's the reason you will almost universally seeing the particle size measurement world that there's this concept of equivalent spheres. And the reason is we have so much difficulty of describing a three-dimensional object using anything but sphere. So using a concept of sphere, we can simplify this description of the particles into, instead of describing by different Feret, Martin, all those different lengths, we'll cut it in half, the area equivalent. So instead, we can use different type of spheres to describe this particle that's shown in the middle. So if you read along those circle, the D of different size and different label, we have D maximum. I'll start from there, which is a sphere having the same maximum length. So you put a sphere surrounding this object, and whatever is the maximum size, maybe that's the diameter you want to use. So it's equivalent sphere of the same maximum length. Or you put into the minimum, right? Sphere of the minimum length. Or like the case of diamond, let's say we use sphere of the same weight. Instead of measuring by shape, we measure by weight, because that's more important, let's say, for us. We want to know about the weight. Or sphere of the same volume. And this is very typical when we are looking at the laser diffraction, as Billy will talk about that tomorrow. When we are looking at the laser diffraction results, we're actually looking at the sphere of the same diffraction, occupying the same volume. or the sphere of the same surface area. And this can be important when we are looking at reactivity, when we are looking at the moisture absorption, the content, surface reactivity. So maybe we're more interested in the size related to the sphere of the same surface area, or sphere passing the same sieve aperture. And this is very typical for powder material processing when we have a sieve, sieving operation. Recognizing the sieve is a flat surface, and if you have a needle shape of particles like showing on the right, what's the governing this particle, whether or not it falls through the sieve? It's the orientation, the minimum diameter that fits in through the sieve, the opening of the sieve. So recognizing basically the particle that you will get doesn't mean that they will have the same, is necessarily exactly the diameter, but rather they will have the same minimum opening that goes through that sieve. So that's the sphere having the same sieve aperture, or sphere with the same diffusion coefficient. That's very common in measurement of the biodynamic light scattering, where we are measuring hydrodynamic radius, or the sphere of the same sedimentation rate. So the bottom line is, in the particle size measurement world, there is this assumption that may not be explicitly mentioned, but you need to recognize it's always there. And it's always, you need to ask, what is underlying assumption? What is the assumed equivalent sphere? And that is, there's always an equivalent sphere in the measurement of the size. And so you need to recognize that, and you need to ask that. So the example on the right shows you, we can have the two particle, one is needle shape, one is a spherical shape, they have the same volume. So if we're measuring by laser diffraction, it will tell you they have relatively similar diameter. But if you look at their shape, if you are more interested in passing a sieve, for example, because it's a solid material operation of a sieving and blending, the fact that they have the same sphere of the same volume may not mean much to you, because they may not go through the sieve in the same way. So that's a point I want to make here, is that always pay attention to what is the technique one, and what's the underlying assumption of the technique, what's the equivalent sphere that is utilizing. So different measurement technique use different equivalent spheres models, so they may not give the same results. Therefore, it's very important, whenever you see a size data, always ask yourself, what is the technique they're used to generate this data? What's the underlying assumption of equivalent spheres? What is that sphere that we are assuming that we're using? So that's about the shape, about the trueness. Now I want to talk about numbers, because when we are describing particle size, we always, of course, talk about what's the technique, what's the underlying assumption of spheres, but also we cannot get away by, we need to talk about the numbers. So what's the number A versus B, right? Whether it meets the specification, what's that number? So when we're looking at number, there's another, some of the, I want you to be aware, kind of challenges, is that unless the material is perfectly monodispersed, there always be a statistical distribution of spread, size. So it's not going to be a unimodal, which typically described by using histogram, right, showing in the middle, this is a spread of the particles. Unless it's a perfect monodispersed sample, which you only have one, in the real world, practically, you will never see a single column distribution, always see this kind of spread. And so this spread described by histogram, which is the frequency of the distribution. And the other equally important curve is this blue dotted line or dashed line is cumulant distribution. So this is essentially its underclass. So D10, D50, D90, you can just draw the horizontal line to indicate whether it's 10%, 50%, or 90% of distribution. So unless, well, in real world, you will never see a perfectly monodispersed material, rather you will see a distribution. Therefore, it's really important when we are describing the numbers about the particles, we always pay attention. There are two sets number we need to provide or you need to know. One set is about the mean, about the average information, right? And the other is a spread. So essentially, if you'll only be presented with one information, which typically the company will provide you the mean value, right? It's not enough because what's frequently critical for the size measurement distribution, equally important as the mean, is the spread, the distribution. But how do we describe, for example, the mean and distribution? So for the mean, there are different type of way to describe the average. So there can be median, which typically means 50% of the particles are smaller than this size, and also 50% are larger than this size. So it's exactly number-wise in the middle. Mode, which is what is the most dominant size across in this sample. And there can be a curve exactly showing on the right, which have multiple peaks, but the highest population of particles may be, so that's the mode. And also, you may describe the particles using a mean value. And this mean value, I will further explain, can have different ways to describe the mean value. So again, the two sets of number, one set is describing mean or average information about the particles, and the other is distribution. Both are equally important. For the distribution, typically what we're looking at is a percentile-based distribution, like D10, D50, D90. That's the reason I see a lot of you asking in your review, asking company, for example, setting three-tiered, acceptance criteria for the particle size distribution. That's really good practice because what you are essentially looking at is this spread, the distribution. But sometimes you may not always get this D10, D50, D90, as we will talk more in the dynamic line scattering. Based on the technique, you may not always generating this percentile-based distribution. Sometimes you need to use a polydispersity index, for example, in dynamic line scattering. So this is another parameter describing the spread, the distribution, and the span is another parameter, which is a D90 minus D10 divided by D50. So it's a compounded number of the three parameters of D10, D50, D90. Again, very useful. And now, also there can be different way to present results, weighing it differently using number, volume, weight, and sometimes different technique naturally using certain different weighing, like imaging technique tend to use a number weighted, whereas dynamic line scattering, as you will hear later, more using the intensity weighted distribution. As showing more, showing on the right, and Bailey will talk more on this about the weighted distribution in the dynamic line scattering. So now I want to talk about means. So as I mentioned earlier, right, when we look at the number, both mean value, average information about particle distribution is important. Also, the spread is important. But now let's just look at the mean. So in this slide, you see there are three particles, exactly three particles. One particle is 1 millimeter, the second particle is 2 millimeter, and the third particle is 3 millimeter. So what I'm going to do, I'm going to calculate the mean value for these three particles using different procedures. So the first one you can see on this first row is number length or arithmetic means. And this is also notation-wise is D10, put into this bracket 1.1, 0. So how do we calculate this? We take the diameter, we adding them together, divided by the three number particles, we get a perfect 2 millimeter. Right, this is a arithmetic mean, easy to calculate. And the second way to calculate mean is by taking the area. So we take the square. Let's say we know this surface area related to the R square. So we just take in the numerator, we take 1 square plus 2 square plus 3 square, and we divide by 3 particles, and then we take the square root. Now we calculate the number area mean being 2.16 millimeter. And the third way to calculate mean is by taking the volume. Let's say we're more concerned about the volume of the particle than the surface area. Then the same way, we take 1 to the third power, 2 to the third power, 3 third power divided by 3 particles, and we take the cubic root of that calculation. We get 2.29 millimeter. And then as you can see, we can further by using other way to calculate mean, D21. So this is, so the 2 and 1 in this within the bracket, what that means is what's on the numerator, what's the power. So if it's a 2, meaning it's to the second, take the square. And the 1 meaning just the number by themselves. If it's 0, meaning only looking at the number of particles. So D21 here, you look at numerator, we have 1 square plus 2 square plus 3 square, and divided by 1 plus 2 plus 3. We get 2.33 millimeter. And D32, we get 2.57. And D43, we get 2.72 millimeter. And the point I want to make here is that, remember, we are still looking at the 3 exactly the same particles. We just calculate the mean using different ways. And all of these ways are correct. And indeed, they are associated with individual measurement techniques. So the D10 number length mean, we typically are looking at microscopy techniques. We look at cryo-TEM, we look at a microscope, and we counted the particles, how many we have measured, we measure diameter. Using this, we calculate the number length mean. So this, inherently, this is what we can only way to measure the microscopy. The other way is area, of course. And then laser diffraction, if you see on the bottom, really you do not know how many particles are in the system. What ended up, what you are only measure is using this volume surface area or volume weighted mean. So you do not need to know how many particles are there, but you just take this third power, second power, or fourth power, third power, and then you can calculate the mean. So each technique inherently assuming a different way to calculate the mean values. So certainly dynamic line scattering use a different way to calculate mean, and it's called intensity weighted harmonic means. So as you can see, each technique, the way to calculate mean values are different. So if I just provide you with one number, let's say the particle size of this material is 2 millimeter. So the question for you is, do you know what the mean value this applicant is providing to you? Do you know what is the technique that used to generate this number? Do you know what is the equivalent sphere that used to generate this number, right? The answer probably is no. Unless you look for this information elsewhere, you will not be able to right away know what that number means. So even you are presented with a mean value, my point is, it has a significant challenge for you to realize how you should evaluate that number, because there are so many different ways to describe means. And a means is only one way, one of the two critical number we need to look at in terms of particle size, and the other is distribution. Okay, so hope you're still here with me. With that, I want to get you some questions. I hope you can follow along. We will go one by one. And I want you to put into the chat, yes or no. The first question, it is important, it's a true statement, true or false. Is it important to know the dispersion medium of particles as it impacts the measurement results in terms of stability, sampling procedure, etc.? Is it true or false? True, 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 true. Correct. It's very true. So thank you. Again, this is one of the aspects about the particle size measurement overlooked. That dispersion medium is really important, because for you as assessor, for the company as a developer of the method, it's really important to know the dispersion medium so that you know something is done properly. The sampling procedure, the dispersion procedure is done properly, because there may be a dissolution happening, there may be crystallization happening, maybe the environment is different, stability is different. So it's true. The second, if sample has stability issue during the measurement, the first sign of the problem can be detected through repeatability measurement. False, false. Should be part of the method. True, 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 true. The answer is true. So the question, how does company know there is a problem, right? That's always, when you're actually developing a method, how do you know there is a problem. You wouldn't know until you see something. So that first sign, there's a problem with stability. Of course, can be by looking just the sample itself. You see before it is a relatively homogeneous dispersion, but very quickly the particles settle down. Of course, there's a sign of problem. It's settling down. But during the measurement, how do we know there's a problem? How do you know as a reviewer there's a problem, right? You will not be able to, in the lab, see how the company is doing the measurement. What you will see is the results provided to you, maybe the repeatability measurement. And you see that from the first run to the last run, the sample is becoming smaller, progressively with time. And that is an indication there's some problem with sample stability. So again, it's true that the sample stability problem can be detected through repeatability measurement. And that's also the reason why we really encourage the company to properly validate the method by showing the repeatability of the method. And the third question, shape of the particle does not impact size measurement results. Is that true or false? Okay, I see everyone is typing false. This one is good. This one is clear. Shape of the particle does impact. What we do is we assume a equivalent sphere of the particles because we have a certain technique need to use to measure the particles, but doesn't mean that all the particles are spherical. And certainly when the particles are not spherical in shape, sometimes it does throw challenges or introduce difficulties during the interpretation of the size measurement results. And one clear example we will show you later is laser diffraction. When the particles are needle-shaped, it presents really difficult challenge for the measurement of the size because shape does matter. The last one, if I gave you this information, do you use false to indicate you are not happy with this value or this statement? Particles in product A has a size value of 200 nanometer. Do you like it? If you don't like it, put false. False, false, false. Great, everyone is really carefully listening. This statement by itself is meaningless. The reason is it only tells you a number, but it didn't tell you how that number is generated, which equipment, which principle, assumption of equivalent spheres, what is the dispersion medium, whether this is a mean or it's a medium or mode, or what type of mean this is. Is this hydrodynamic, using the dynamic light scattering, so it's an intensity weighted harmonic means, or is this obtained by cryo-TEM, so maybe this is a number length mean. So by looking at the number itself, there's difficulty to know really what this number is, right? So in your review, if you see this type of statement, think about, and is that right? Maybe not right. And then now what you need to do is go into some other places in the package, in the document, to search for the information that are missing. Can you piece together information? Can you find the information that is not described, but maybe critical, right? So again, never just by looking at the number itself, thinking, okay, the company has a good handle on their procedure or their reporting. There are a lot of information that's missing in this statement about just simply providing a number. Okay, to summarize, I want to make it even more challenging for you because this is really indeed what happened in our research. As good as I can teach you about how to measure size, how challenging we already recognize measurement of size, how we recognize it's difficult to measure, to state what is true about the particles. In reality, there's even a greater challenge about recognizing what we are actually measuring to interpret and make a decision. So I will borrow this story. I know everyone is very familiar with story about the elephant and six blind men, where everyone is touching one places and they are describing what they perceive as the elephant, right? So there's another perspective about the particle size measurement that's very easy to understand when I show you this data. So this is the same material. We measure by different techniques. So the first technique, dynamic light scattering, we get a Z average value about 118 nanometer. The second technique, we're measuring by laser diffraction. We generated a volume-weighted mean value of 96 nanometer. And the third technique we're using is cryo-TEM, which is looking at the particles directly measured diameter. We get a number of 26 nanometer plus minus 14 nanometer. And the next example, we're using nanoparticle tracking analysis, tracking the movement of the particles and calculating the Brownian motion, diffusion coefficient, calculating the mean value, D50. This is medium, right? D50 percentile, 108 nanometer. And also we use DOSY NMR, calculating again diffusion coefficient and using diffusion coefficient to calculating the diameter using Stokes-Einstein equation, about 70 nanometer, the mean value. And by using a separation technique, Hayo will talk about more on the AF4, we separate all the particles and we measure them separately, and we get, okay, we get one population 30 to 80 nanometer, another population about 100 nanometer, but we got two populations. So the question is, which of this measurement is correct, or which measurement is not correct, right? The answer is all of them are correct, but all of them are wrong at the same time, because each technique has its own limitations. It only provides you the information, the technique, the assumptions, how that instrument is measuring. And we cannot directly compare one measurement by one technique to another measurement, right? We cannot compare Z average from DLS to cryo-TEM, because those are two totally different techniques. Those are two totally different mean values. And those mean value, as I showed you earlier, is reasonable for them to be different. Of course, what is the risk of relying on a single technique to get understanding? It's really high risk. All right, so through this example, what I'm showing you, this is a cyclosporine ophthalmic emulsions. We measured many samples using different techniques. Eventually, over time, we accumulated more understanding about the measurement. We recognize how much we actually don't know about the measurement of the particle size. And can we trust the technique if we have sufficient understanding? The short answer for that is yes. With thousands of measurements, now we know what we are doing. We know why the difference exists. Therefore, we feel more comfortable trusting a single technique. Of course, why do we care about the measurement in the first place, right? I mentioned before, what we are truly interested is actually not the size. Even though what I'm showing on this screen, so many numbers, but those are not what we truly interested. What we're truly interested in the globule size in this example is how likely the globule size distribution impacted the distribution of the drug, how likely the size impacted the bioavailability of the drug, in a sense, drug release. So we care about the size because we care about other things that is more important to what does this particle do? Why is this particle formed in this way in the first place? So that goes back to my beginning when I mentioned about what we are truly interested is not the size. That concludes the portion on the particle size concept. The last few minutes, I will just quickly go through the scattering phenomenon, and you will hear more in the dynamic light scattering portion and also laser diffraction portion. So overall, what is a light scattering? Light scattering is interaction of a light with the particles. We know light is both wave and a particle. So we interact with another particle through this interaction, both constructive and destructive. And when we shine an incident light, if you look at the bottom of the graph, to a particle in this waveform, and when this wave hits the particle, it's going to interact, induce oscillation dipole in the electron cloud of this particle, which then will radiate energy in different directions, all directions. And this radiated energy is called a scatter light. So when you shine a light to a particle, this particle will scatter light basically to all directions. And this is very well understood concept. Indeed, two very commonly used theory to describe this scattering phenomenon. One is Rayleigh scattering, the other is Mie scattering. This has to do with the relative dimension of the particle to the wavelength of the light. And there are really two ways to study this scattering phenomenon. One way is look at the time-dependent changes of the scattering signal as a function of time. So it's time dependent. So this way, it's a basis of dynamic light scattering, DLS, that we will talk about the next presentation. And the other way to analyze scattering phenomenon is by assessing the scattering intensity as a function of angle. So you put a sensor at surrounding this particle at a different angles, some at the forward, some at the 90 degree, some at 180 or 170 degree, and you measure the intensity as a function of a scattering angle. This is angular dependent measurement. So this is what formed the basis for laser diffraction or static light scattering. So two ways to study the light scattering phenomenon: time dependent, which is dynamic light scattering; angular dependent, which is static light scattering or laser diffraction. And for the Rayleigh scattering, it has to do with the scattering when the particle is smaller than 1/10 of the wavelength. So typically scatter light in all directions, isotropic. And for our measurement, for example, in the Marvin zetasizer, that means if the particle is below 60 nanometer, we can perfectly assume a Rayleigh scattering in all directions. We can get same scattering intensity. For the Rayleigh scattering, there's this formula to the bottom of the screen. I don't need you to remember this equation, but the thing I want to point it out is within this equation, there's I, which is scattering intensity, and D, which is the size of the particles. You see this intensity of the scattered light as a function of the particle size is to the 6th power. So what that means is if you have one speck of large particle in the presence of 10,000 smaller particles, and this one single large speck of larger particle will contribute to more of the scattering intensity than 10,000 of smaller particles. The reason being the intensity of scattered light is to the 6th power of the particle size. And this is where this phrase, you may heard it many times. This is where it comes from Rayleigh's approximation, and this equation tells you why. And also this is reason, this equation explains the reason why the sky is blue, right? Why the sky blue is because the angle where we're looking at, we are mostly looking at the scatter light. We're not directly looking at the sun, which is light source. We're looking at an angle maybe 90 degrees to where the light, the sun is shining. So we're looking at mostly the scatter light. And if you look at the spectrum to the right, the blue light, which is lower wavelengths, if you see in the equation, the wavelength of light is in the denominator to the 4th power. Essentially, the shorter wavelength of the light will have more scattered, will be more scattered. Therefore, the blue light is mostly being scattered. Therefore, we have this background of the light sky appearing in blue color, because in the air, it's not entirely pure. We have a lot of dust particles. So those particles will scatter light. Again, contribute to the blue light. And for the same reason, during the sunset or sunrise, we see the sky as red. The reason is when during sunrise or during sunset, where we are looking at is directly at the light source, we're looking at what's remaining of the light. Because most of the blue light has been scattered, we're only looking at the light which remaining, mostly the yellow to red domain. So we have seen the sky appear mostly yellow and red. So some interesting fact about this equation essentially can help you understand a lot about the daily lives. Last bit, we look at the Mie theory, which is a little bit more complicated. It's the exact solution to Maxwell equation. Until we have computers, it's really difficult to solve the equations. That's the reason that's mostly used in the laser diffraction measurement. The computers programming using iterative calculation to perform this calculation to give you the size value. So this is mostly dealing with the scattering as a function of scattering angle, so especially when the size of the particles approaches the wavelength of the light or slightly larger than the wavelength of the light. It's going to result in the scattering intensity at different measuring angle, resulting different maximum and minimum. So when you place a sensor at different locations, you will see some sensor has a higher amount, some sensor has a lower amount. You are able to construct a diffractogram, which is then used to calculate through complicated equations what is the original source of the particle result in the scattering pattern. So what's showing at the bottom right, this is the mean scattering for the larger particles when the size is approaching the wavelength of light. And again, by placing the sensor at different scattering angle, you can get the size results through that. So that concludes this first session of particle size concept and light scattering phenomenon. Thank you all for staying with us. And I think we will have a short break before we start the next session, which is dynamic light scattering. I will stick around if you want to ask a few questions, but otherwise we will have about 5 minutes break. Thank you, everyone.